Every star you see tonight is moving in a way that shouldn't be possible. Right now, as you read these words, our sun is hurtling through space at 230 kilometers per second, over 500,000 miles per hour. It's racing around the center of the Milky Way galaxy, completing one orbit every 225 million years. And it's not alone. 200 billion stars are all performing this cosmic dance, their motions choreographed by forces we're only beginning to understand. In the 1970s, an astronomer named Vera Rubin pointed her telescope at distant spiral galaxies and discovered something that shattered everything physicists thought they knew about how the universe works. The stars she observed were moving far too fast. According to every law of physics, according to centuries of mathematical certainty, those stars should have been flung into the darkness of intergalactic space billions of years ago. But they weren't. They held together, spinning at impossible speeds, as if gripped by invisible hands. What she discovered that night would lead to one of the greatest mysteries in modern science. A mystery that remains unsolved today. A mystery about what's really controlling the motion of every star in the universe. To understand why Rubin's discovery was so shocking, we need to start with what we expected to find. And that expectation came from the most elegant observations in the history of astronomy. In the early 1600s, Johannes Kepler discovered 3 laws describing planetary motion. The most important for our story is his third law. Planets farther from the Sun move slower in their orbits. Mercury, the innermost planet, screams around the Sun at 47 kilometers per second, completing an orbit in just 88 days. Earth, farther out, moves at a more leisurely 30 kilometers per second, taking 365 days to complete its journey. Neptune, at the outer edge of our solar system, crawls along at just 5.4 kilometers per second, requiring 165 Earth years for a single orbit. This makes perfect sense. It's basic physics. Isaac Newton explained why with his law of universal gravitation in 1687. The Sun contains 99.86% of all the mass in our solar system. Its gravitational pull decreases with distance. Objects farther away feel less gravitational force, so they orbit more slowly. The mathematics is elegant and precise. If you know the mass of the central object and the distance of the orbiting object, you can calculate exactly how fast it should be moving. The equation is simple. Orbital velocity should decrease with the square root of distance. This isn't just theory. We've tested it countless times. Every planet, every moon, every artificial satellite orbiting Earth follows this rule with perfect precision. Launch a satellite into a higher orbit, and it automatically slows down. Move it to a lower orbit, and it speeds up. The equation never fails. When astronomers began studying galaxies in detail, they naturally assumed the same physics would apply. A galaxy is essentially a massive collection of stars orbiting a common center, just like planets orbit the Sun. The mass is more spread out, yes, but the principles should be identical. Most of a galaxy's visible mass, the stars you can actually see, is concentrated toward the center. This means stars in the outer regions should behave like Neptune. Distant from most of the mass, they should orbit slowly. The prediction was clear. The math was certain. The physics was settled. But when astronomers pointed their telescopes at distant galaxies, Vera Rubin wasn't looking to overturn physics. In the 1970s, she and her colleague Kent Ford were simply trying to measure how fast stars orbit in spiral galaxies. It was supposed to be straightforward observational astronomy: collect data, confirm what everyone already knew, publish, move on. They pointed their instruments at the Andromeda galaxy, our nearest large galactic neighbor, and began measuring the velocities of stars at various distances from the galactic center. They used the Doppler shift, the same effect that makes an ambulance siren change pitch as it passes you, to determine how fast stars were moving. The inner stars behaved as expected. They were moving quickly, as predicted by Newton's laws. But as Rubin and Ford measured stars farther and farther from the galactic center, something strange happened. The stars didn't slow down. They measured stars at the galaxy's visible edge, where almost no stars or glowing gas could be seen. These stars should have been moving at perhaps 50 kilometers per second, maybe less. Instead, they were racing along at over 200 kilometers per second. Rubin checked her instruments. She rechecked her calculations. She measured other galaxies. The same impossible pattern appeared everywhere she looked. Stars at the outer edges of galaxies were moving 2, 3, even 4 times faster than they should be, not just in one galaxy, in every galaxy she observed. The rotation curves, graphs showing orbital velocity versus distance from the center, were flat instead of declining. This was the flat rotation curve problem, and it made no sense whatsoever. According to the visible mass distribution and Newton's laws, stars in the outer regions of the Andromeda galaxy should be moving around 50 to 80 kilometers per second. Instead, they were clocking in at 200 to 250 kilometers per second. The difference was staggering, and this wasn't a subtle discrepancy. This wasn't a small measurement error or a minor correction to theory. The stars were moving so fast that by all rights, they should have escaped the galaxy's gravitational pull billions of years ago. They should have been flung into intergalactic space like water droplets flying off a spinning wheel. But they weren't. The galaxies held together, defying explanation. Imagine spinning pizza dough. When you toss it in the air and spin it, the outer edge stretches and eventually flies away because there's not enough strength in the dough to hold it together against the centrifugal force. That's exactly what should happen to galaxies. Stars at the outer edges are experiencing tremendous centrifugal force from their high-speed orbital motion. The only thing preventing them from flying away is the gravitational pull from all the mass in the galaxy. But here's the problem. When you add up all the visible mass in a galaxy, all the stars you can see, all the glowing gas, all the dust, there's simply not enough gravity to hold those outer stars in place at the speeds they're actually moving. The math doesn't work. It's not even close. The visible mass in a typical spiral galaxy can account for maybe 10 to 20% of the gravitational force needed to keep those outer stars in their orbits. The rest, 80 to 90% of the required mass, is simply missing. It's not there, at least not in any form we can see. Let me put this in perspective. If you tried to drive a car around a circular track at high speed, the friction between your tires and the road provides the inward force needed to keep you moving in a circle. Remove that friction and you'd shoot straight off the track into the infield. That's the situation with galaxies. The outer stars are moving so fast that the visible mass provides only a fraction of the friction, the gravitational grip, needed to keep them on their circular paths. They should be shooting off into space. But they're not, and this wasn't even a new problem. In 1933, 4 decades before Rubin's observations, a Swiss astronomer named Fritz Zwicky studied the Coma Cluster, a group of over 1,000 galaxies bound together by gravity. He measured how fast the galaxies were moving relative to each other and calculated how much mass the cluster needed to keep them gravitationally bound. The answer shocked him. The cluster needed about 400 times more mass than he could account for from visible stars and gas. He called this invisible material dunkle Materie, dark matter. Most physicists dismissed Zwicky's findings. Maybe his measurements were wrong. Maybe he'd made a calculation error. The idea that 90% of the universe's mass could be invisible seemed absurd. But Rubin's rotation curves confirmed it. The missing mass problem was real, and it existed in every galaxy ever observed. There's only one explanation that fits the data. Something invisible is out there, surrounding every galaxy, providing the gravitational grip that keeps outer stars from escaping. This invisible mass doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation in any detectable way. It's completely transparent to every form of light we've ever discovered. Radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays, all of it passes through this material as if it weren't there. But it has mass, and mass means gravity, and gravity is what's controlling the motion of every star. When you look at a galaxy, you're seeing only a small fraction of what's actually there. The beautiful spiral arms, the bright galactic core, the glowing gas clouds, all of that visible structure is just the tip of the iceberg. Surrounding it, extending far beyond the visible edge, is a massive spherical halo of this invisible material. This dark matter halo is what's really holding the galaxy together. It provides the gravitational scaffolding that keeps stars in their orbits. Without it, galaxies would simply fly apart. And it's not just a few galaxies. Every galaxy ever studied shows the same pattern: small dwarf galaxies, medium spiral galaxies like our Milky Way, giant elliptical galaxies. All of them are embedded in dark matter halos that contain far more mass than all their visible stars combined. Our own Milky Way is no exception. Right now, you're sitting inside a vast invisible ocean. The Sun, Earth, and everything you've ever known exists within a dark matter halo that extends hundreds of thousands of light years in every direction. This halo contains roughly 1 trillion times the mass of our Sun, 10 times more mass than all the visible stars in our galaxy. 200 billion stars, including our Sun, are all dancing to the gravitational tune played by this invisible conductor. Their speeds, their orbits, their motions through space, all of it is controlled primarily by matter we cannot see, cannot touch, and still don't fully understand. What is this invisible force? The answer is stranger than anyone imagined. The universe is drowning in something we cannot see. Think about that for a moment. Every galaxy you've ever seen in a photograph, those spectacular spirals, those elegant ellipticals, those irregular clouds of stars, they're all floating in an invisible ocean. An ocean so vast, so massive, that it makes the visible stars look like tiny boats bobbing on an endless sea. When astronomers finally accepted what the rotation curves were telling them, they faced an uncomfortable truth. 95% of the mass in every galaxy is completely invisible, not hidden behind dust, not too faint to detect, literally invisible, made of something that doesn't interact with light at all. They called it dark matter, though that name is misleading. It's not matter that it happens to be dark. It's not regular atoms that simply aren't glowing. It's something fundamentally different from every particle we've ever studied in a laboratory. So, what is this invisible ocean made of? That question has haunted physics for half a century. And the answer, or rather the lack of an answer, is one of the most profound mysteries in science. Before we dive into what dark matter might be, let's be clear about one thing. Dark matter is real. This isn't speculation or theoretical hand-waving. The evidence is overwhelming, coming from multiple independent lines of observation that all point to the same conclusion. First, there are the rotation curves themselves. Vera Rubin's discovery wasn't a fluke or limited to a few weird galaxies. Every spiral galaxy astronomers have studied, and we're talking thousands of them, shows the same flat rotation curve. Stars at the outer edges moving far faster than visible matter alone can explain. The pattern is universal, but rotation curves are just the beginning. In 1979, astronomers discovered something called gravitational lensing around galaxies. Einstein predicted this. Massive objects bend spacetime, which bends light passing nearby. When you look at a distant galaxy with a closer galaxy in front of it, the background galaxy's light gets warped and distorted by the foreground galaxy's gravity. Here's the thing. When astronomers measure how much the light bends, they can calculate exactly how much mass is doing the bending. And every single time, the answer comes back the same. There's far more mass present than the visible stars, and gas can account for. the lensing is so strong that invisible matter must be creating most of the gravitational field. Then came 2006, and the observation that changed everything, the bullet cluster. Two massive galaxy clusters had collided and passed through each other at millions of miles per hour. When astronomers studied the aftermath, they saw something extraordinary. The hot gas, the normal matter that makes up most of the visible mass in galaxy clusters, had collided during the passage. You could see it glowing in X-rays, slowed down and bunched up in the middle, where the collision happened, like two cars crashing into each other. But when they measured where most of the mass actually was using gravitational lensing, they found something shocking. The majority of the mass hadn't slowed down at all. It had passed right through, as if the collision never happened. The dark matter in each cluster had ghosted straight through the other cluster's dark matter, completely unaffected. This was the smoking gun. It showed, visually and undeniably, that dark matter and normal matter are separate things. The normal matter collided and slowed. The dark matter didn't. You could literally see the separation in the images, the glowing gas in one location, the gravitational lensing showing mass in another. Since the bullet cluster, astronomers have found similar evidence in other colliding clusters. Every observation confirms the same picture. Galaxies are surrounded by massive halos of invisible matter. These halos don't glow, don't emit any light, and barely interact with normal matter at all, except through gravity. The stars we see, the gas that glows, the planets and dust and everything made of atoms, it's all just a tiny fraction of what's actually there. We're living in a galaxy that's mostly invisible. So if dark matter is real, what is it? Let's start by eliminating the obvious candidates, because scientists have spent decades ruling out everything normal. Could it be black holes? At first, this seemed promising. Black holes are invisible and have mass, exactly what we need. But the numbers don't work. To account for all the dark matter, you'd need an absurd number of black holes scattered throughout every galaxy. And here's the problem. Black holes create distinctive gravitational lensing effects. We'd see them. Astronomers have looked, and there simply aren't enough black holes to explain dark matter. Not even close. What about dead stars, white dwarfs, neutron stars, black dwarfs, or brown dwarfs that never quite ignited? These objects are collectively called MACOs, massive, compact halo objects. Again, sounds promising. They're made of normal matter but don't shine brightly. Scientists tested this idea with something called microlensing surveys. The concept is clever. If a MACO passes between us and a distant star, its gravity should briefly brighten that star's light as it acts like a lens. So astronomers monitored millions of stars for years, watching for these telltale brightening events. The result? MACOs exist, but there aren't nearly enough of them. The surveys found some brown dwarfs and other dim objects, but they account for maybe 20% of the dark matter at most. The vast majority of dark matter can't be MACOs. Could it be planets, asteroids, rogue worlds drifting between the stars? Same problem. Not enough of them, and they'd still show up in microlensing surveys. What if it's just normal matter that happens to be cold and dark, like vast clouds of molecular hydrogen that don't emit light? Nope. We can detect cold hydrogen through other means, like radio observations. And besides, there's a more fundamental problem. The physics of the early universe tells us exactly how much normal matter, the kind made of protons, neutrons, and electrons, could have formed after the Big Bang. That number is fixed by observations of the cosmic microwave background radiation, and it's way too small to account for dark matter. Dark matter isn't black holes. It's not dead stars. It's not planets or dust or cold gas. It's not any form of normal atomic matter that's simply hiding. It's something exotic, something that barely interacts with light or normal matter at all. Something that, as far as we can tell, only reveals itself through gravity. So we know dark matter exists, and we know it's not made of normal stuff. But where is it exactly? And how much of it is there? The answer is both elegant and unsettling. Every galaxy sits inside a massive spherical cloud of dark matter called a halo. These halos are enormous, far larger than the visible galaxy itself. The Milky Way's luminous disk, the part you can see stretching across the night sky, extends about 100,000 light-years from edge to edge. But the dark matter halo, it reaches out to at least 600,000 light-years, possibly even farther. Our galaxy is a small island of light floating in a dark matter ocean 6 times wider. And it's not just bigger, it's vastly more massive. The visible matter in the Milky Way, all 200 billion stars, all the gas and dust, everything that glows or reflects light, adds up to roughly 100 billion times the mass of our Sun. That sounds like a lot. It is a lot. But it's nothing compared to the dark matter halo. Current estimates put the dark matter mass at around 1 trillion solar masses. That's 10 times more than all the visible matter combined. Some estimates go even higher, suggesting the ratio might be closer to 100 to 1. Let that sink in. For every kilogram of normal matter in our galaxy, every atom in every star, every molecule in every gas cloud, there are 10 to 100 kilograms of dark matter surrounding it. We are the minority. Normal matter is the strange exception. Dark matter is what the universe is mostly made of. This invisible ocean isn't uniform though. It's densest near the center of the galaxy and gradually thins out as you move toward the edges. But even at the Sun's position, 26,000 light-years from the galactic center, we're swimming through dark matter. It's passing through this room right now, passing through your body, completely unnoticed. Billions of dark matter particles flow through every square centimeter every second, and we don't feel a thing because they barely interact with normal matter. Every star in the galaxy orbits within this halo. The dark matter provides the gravitational scaffolding, the background potential that keeps everything bound together. Without it, the outer stars would have been flung away billions of years ago. The galaxy would have flown apart. The visible galaxy, all those beautiful spiral arms, all those brilliant stars, is just the foam on top of an invisible wave. So, what is dark matter actually made of? After decades of research, the honest answer is, we don't know. But scientists have some educated guesses. The leading candidates are exotic particles that don't exist in the standard model of particle physics. Particles we've never detected in any laboratory experiment. The most popular candidate goes by the awkward acronym WIMPs, Weakly Interacting Massive Particles. These hypothetical particles would be heavy, perhaps 10 to 1,000 times the mass of a proton. But they'd interact with normal matter only through gravity and possibly through the weak nuclear force. That would make them incredibly difficult to detect. Scientists have built massive detectors deep underground, places like the Large Underground Xenon experiment in South Dakota, buried a mile beneath the surface to shield it from cosmic rays. These detectors contain tanks of ultra-pure liquid xenon, kept at incredibly cold temperatures, constantly monitored for the telltale sign of a dark matter particle colliding with a xenon nucleus. They've been running for decades. So far, nothing. Not a single confirmed detection. Another candidate is the axion, a hypothetical ultralight particle billions of times lighter than an electron. Axions were originally proposed to solve a different problem in particle physics, but they happen to have the right properties to be dark matter. If they exist, there would be trillions upon trillions of them streaming through space, collectively providing the gravitational pull we observe. Then there are sterile neutrinos, theoretical cousins of the known neutrinos, but much heavier and even more reclusive. The truth is, we're searching for something we can barely imagine. Dark matter could be any of these particles, or something completely different that no theorist has thought of yet. It's one of the greatest mysteries in physics. We know it's out there, we can measure its effects with exquisite precision, but we can't figure out what it's made of. Imagine discovering that your house sits on an invisible foundation 10 times larger than the house itself, holding everything up, and not being able to figure out what that foundation is made of. That's where we are with dark matter. But here's what makes this mystery even more fascinating. Dark matter isn't the only invisible force controlling stellar motion. There's something else at the heart of every galaxy. Something we can't see, but for a very different reason. Something monstrous. At the heart of every galaxy lurks something monstrous. A supermassive black hole. An abyss so dense that nothing, not even light, can escape once it crosses the point of no return. These cosmic predators contain millions, sometimes billions of times more mass than our Sun, all crushed into a region smaller than our solar system. And they're everywhere. The Milky Way has one, Andromeda has one, M87 has one so massive it contains 6.5 billion times the Sun's mass. The first black hole ever photographed, its shadow looming against a glowing ring of doomed matter. Every major galaxy astronomers have studied harbors one of these monsters at its center. For decades, the story seemed obvious. These black holes must be running the show. After all, they sit right at the gravitational center of their galaxies. Surely all those billions of stars are orbiting around them, held captive by their immense gravity, like planets circling a sun but on a galactic scale. It's an intuitive picture. It feels right. What could possibly compete with the gravitational pull of a black hole millions of times more massive than the Sun? But here's the uncomfortable truth. That entire picture is wrong. Supermassive black holes don't control their galaxies. For the vast majority of stars, including our own Sun, the central black hole might as well not exist. Its gravitational influence is so localized, so negligible beyond a tiny region, that it plays almost no role in determining how stars move. So, what are these monsters actually doing? And if they're not in control, what is? To understand the truth about supermassive black holes, we need to meet the one at the center of our galaxy. Its name is Sagittarius A, pronounced Sagittarius A star, and it lives approximately 26,000 light-years from Earth, buried behind thick clouds of dust and gas that make the galactic center invisible to ordinary telescopes. You can't see its invisible light. The view is completely blocked. But starting in the 1990s, two teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute in Germany, the other by Andrea Ghez at UCLA, began using infrared telescopes to peer through the dust. What they were looking for were stars. Not the black hole itself, which is invisible, but the stars orbiting near it. And what they discovered was extraordinary. They tracked individual stars year after year, mapping their positions with exquisite precision. They watched these stars move, completing parts of their orbits, some taking decades to swing around the center. They compiled the data into animations showing the stellar dance around an invisible point. One star became particularly famous, S2, also called S-Erosion 2, depending on which team named it first. S2 orbits Sagittarius A once every 16 years. We've now watched it complete multiple full orbits, and the orbit is extreme. At its closest approach, called periapsis, S2 screams past the black hole at roughly 5,000 kilometers per second. That's nearly 2% the speed of light. It approaches within about 17 light hours of the event horizon, closer than Neptune is to our Sun. Then it swings outward in a highly elliptical orbit, reaching a distance of more than 1,500 light hours before falling back in again. The precision of these observations is staggering. Astronomers can measure S2's position to within a few milliarc seconds. That's like distinguishing a quarter in Los Angeles from a telescope in New York. And S2's motion matches Einstein's predictions perfectly. The orbit processes, its orientation shifts slightly with each pass, exactly as general relativity predicts for an object moving that fast in such a strong gravitational field. There's only one explanation for this behavior. S2 is orbiting something with approximately 4.3 million times the mass of the Sun, compressed into a region so small it can't be anything except a black hole. Other stars near the galactic center show similar behavior. S62 has an even more extreme orbit, approaching to within just 16 light hours and reaching speeds up to 8% the speed of light. These stars provide undeniable proof that Sagittarius A*s exists. For this work, Genzel and Ghez shared the 2020 Nobel Prize in Physics, along with Roger Penrose for his theoretical work on black holes. The observations were that important. They confirmed that supermassive black holes aren't just theoretical, they're real. They're at the centers of galaxies, and we can map them with extraordinary precision. So, there it sits, a monster with 4.3 million solar masses, anchored at the gravitational center of our galaxy. Surely this must be what holds everything together. Surely our Sun, 26,000 light-years away, is orbiting this massive object, right? Not even close. Here's the mental model most people carry. The supermassive black hole sits at the center like a cosmic anchor, and all the stars in the galaxy orbit around it. Just like planets orbit the Sun, stars orbit the black hole. It's the central mass holding everything in place. This is fundamentally wrong, and the reason why reveals something important about how galaxies actually work. Let's look at the numbers. Sagittarius A sighting contains 4.3 million solar masses. That sounds enormous. It is enormous by any normal standard. It's millions of times more massive than our Sun, thousands of times more massive than any stellar mass black hole formed from a single star. But now compare it to the galaxy as a whole. The Milky Way contains roughly 100 billion solar masses of visible matter, stars, gas, dust, everything that emits or reflects light. And as we learned in the previous chapter, the galaxy is surrounded by a dark matter halo containing approximately 1 trillion solar masses. Do the math. The black hole represents about 0.01% of the galaxy's total mass. It's a rounding error. It's like a grain of sand on a beach, a drop of water in an ocean. You don't orbit a grain of sand, you can't. It doesn't have enough mass to gravitationally dominate anything except its immediate vicinity. What stars actually orbit, including our Sun, is the combined center of mass of the entire galaxy. Every kilogram of matter contributes. The dark matter halo, the disk of stars and gas, the central bulge, yes, even the black hole. But the black hole is just one tiny contributor among countless others. Here's an analogy. Imagine 3 people holding hands in a circle, spinning around together. They're all orbiting their mutual center of mass, the point in the middle of their triangle. Now imagine one of them is wearing a heavy ring on their finger. That ring sits near the center of their rotation, because the person wearing it contributes more mass. But the ring itself isn't what they're orbiting around. It's just along for the ride, sitting near the center because of where physics naturally puts the densest object. The black hole is the ring. So where does the black hole's gravity actually matter? Only in the innermost few light years of the galaxy, a tiny, tiny fraction of the galactic radius. Within that region, stars like S2 genuinely do orbit the black hole. Their motion is dominated by its gravity because they're close enough that the black hole's 4.3 million solar masses is more important than anything else nearby. But beyond about 10 light years, the black hole's influence becomes negligible. The gravitational pull from the billions of stars in the bulge, the trillions of solar masses in the dark matter halo, the stars in the disk, all of that collectively overwhelms the black hole's gravity. Our Sun orbits 26,000 light-years from the galactic center. At that distance, the gravitational force from Sagittarius AE is utterly insignificant. If the black hole magically disappeared tomorrow, just vanished, our orbit wouldn't change at all. We wouldn't even notice. The central black hole isn't controlling the galaxy. It's not the gravitational anchor. It's a passenger sitting at the center, impressive and destructive in its own right, but fundamentally irrelevant to the motion of almost every star in the galaxy. So, if the black hole doesn't control the inner galaxy, what does? The answer is the galactic bulge, a dense, roughly spherical swarm of old stars concentrated around the center. This is where the real mass lives. This is what actually matters gravitationally in the inner regions of the galaxy. The Milky Way's bulge extends out to approximately 2,000 light years, 2 kiloparsecs in astronomical units, from the galactic center. It's a chaotic, crowded place, nothing like the orderly disk where we live, and it contains roughly 20 billion solar masses worth of stars. Let's pause on that comparison. The black hole, 4.3 million solar masses. The bulge, 20 billion solar masses. The bulge outweighs the black hole by a factor of nearly 5,000 to 1. This is what controls stellar orbits in the inner galaxy. Not the black hole, but this massive concentration of billions of ancient stars, all contributing their gravity, creating a deep potential well that dominates the region. And the bulge isn't just massive, it's incredibly dense. Out here near the Sun, the nearest star is over 4 light years away. Proxima Centauri, our closest neighbor, is an unimaginably lonely 4.24 light years distant. Space between stars is mostly empty. In the bulge, stars can be separated by just thousands of astronomical units, the kind of distances we measure inside our solar system. If you lived on a planet in the bulge, your night sky would be spectacular. Brilliant stars packed together, some appearing as bright as Venus does from Earth, dozens of them scattered across the sky. But that crowding has consequences. Stars in the bulge regularly have close encounters with each other. Studies suggest roughly 80% of bulge stars will pass within 1,000 AU of another star during their lifetimes. For comparison, such an encounter out here in the disk is virtually impossible over the entire 13.8 billion year history of the universe. These encounters perturb orbits, transferring energy and angular momentum between stars. The result is gravitational chaos. Unlike disk stars, which all orbit in the same direction in neat, organized circles, bulge stars move every which way. Some plunge toward the center and swing back out. Others loop around on tilted orbits. There's no coherent rotation, just a chaotic swarm of stars moving in every conceivable direction, their collective gravity binding them together. This is what dominates the inner galaxy. For any star within a few thousand light years of the center, it's not the black hole controlling its motion. It's the immense collective gravitational field of 20 billion stars in the bulge, all pulling on each other, creating a complex potential that determines where everything goes. The black hole is just one object among 20 billion. Admittedly an extreme object, but statistically irrelevant to most of them. So, here's what we've learned. Supermassive black holes don't control their galaxies. They don't steer the ship. They're not the gravitational anchor, they're passengers. And yet, there's something intriguing going on. Astronomers have discovered a remarkably tight correlation between the mass of a galaxy's central black hole and the mass of its bulge. Bigger bulges tend to have bigger black holes. The relationship isn't perfect, but it's strong enough that you can estimate a black hole's mass reasonably well just by measuring the bulge mass. This tells us something important. Black holes and galaxies grow together. They co-evolve. When galaxies merge, when two galaxies collide and combine, gas gets funneled toward the center by the gravitational chaos. That gas feeds both star formation in the bulge and accretion onto the central black hole. Both grow simultaneously. The black hole and the galaxy are linked in their history, even if the black hole doesn't control the galaxy's present-day dynamics. It's like a celebrity who takes credit for a team victory. The black hole sits at the center, dramatic and attention-grabbing, and it's easy to assume it's running everything. But the real work, the gravitational heavy lifting, is being done by everyone else. The dark matter halo, the bulge, the disk, all contributing their mass, all creating the potential that actually controls stellar motion. In the innermost few light years, yes, the black hole dominates. Stars like S2 genuinely orbit it, their paths controlled by its concentrated mass. But that's a tiny region. For the remaining 99.99% of the galaxy, for the 200 billion stars scattered across hundreds of thousands of light years, the black hole is irrelevant. It's a passenger, not a driver. So we've now solved several pieces of the puzzle. Dark matter controls the outer regions, providing the gravitational scaffolding that keeps the rotation curve flat far beyond the visible edge. The bulge controls the inner regions with its 20 billion solar masses of ancient stars. And the black hole? It matters only at the very center, and even there, it's a minor player in the grand scheme. But there's still something missing. Between the dark matter halo extending hundreds of thousands of light years and the bulge concentrated in the inner few thousand light years, there's a huge middle ground, the galactic disk, where most of the visible stars live, where our sun orbits, where the spiral arms sweep through space. What controls the motion of stars there? What determines our sun's 230 km/s velocity around the galactic center? If dark matter sets the overall potential, and the bulge controls the inner region, and the black hole barely matters, what's governing everything in between? That's the question we need to answer next. Between the dark matter halo extending hundreds of thousands of light years and the central bulge packed into a few thousand light years, there lies everything we can actually see, the visible matter that makes up the galaxy's disk. This is the part of the galaxy we're most familiar with. The spiral arms stretching across space, the glowing clouds of gas where new stars are born, the 200 billion stars scattered across a vast rotating plane, including our own sun. When you look up at the Milky Way on a dark night, you're seeing a cross-section of this disk from the inside. But here's what most people don't realize. Even though this visible matter is what we see, what we study, what we photograph, it's still not what's controlling most of the motion. The disk is gravitationally important, don't get me wrong. The stars and gas in the disk do influence each other's orbits. They do contribute to the overall gravitational potential, but they're not the dominant force that we might expect them to be. So how much does visible matter actually contribute to stellar motion? Where does its influence begin and end? And how does it fit into the bigger picture with dark matter and the bulge? To answer these questions, we need to break down the visible mass of our galaxy piece by piece. Let's start with the stars themselves. Roughly 200 billion of them spread across the galactic disk. These stars contain a combined mass of approximately 100 billion times the mass of our Sun. That's an almost incomprehensible amount of matter. If you could somehow gather all those stars together, they'd outweigh our Sun by a factor of 100 billion. But the disk is enormous, so that mass is spread thin. The Milky Way stellar disk extends out to about 80,000 to 100,000 light years in diameter, though it fades gradually at the edges rather than having a sharp boundary. The distribution follows what astronomers call an exponential density profile. It's densest near the center and gradually becomes sparser as you move outward. There's no sudden drop-off, just a steady thinning. The thickness of the disk varies, but it's surprisingly thin compared to its width. Near the Sun, the disk is only about 1,000 light years thick. That's a ratio of about 100.1, like a dinner plate compared to its diameter. We live in a cosmic pancake. And almost all these stars are moving in the same direction, in nearly circular orbits around the galactic center. This is very different from the chaotic, randomized orbits in the bulge. Disk stars are organized, orderly, all participating in the same rotating flow. Our Sun is one of those disk stars. We're located about 26,000 light-years from the galactic center, roughly halfway out, sometimes described as being in the galactic suburbs. And we're moving fast. The Sun orbits the galactic center at approximately 230 kilometers per second. Think about that for a moment. We're not just sitting still in space while Earth orbits us. The entire solar system, sun, planets, asteroids, comets, all of it, is racing around the galaxy at 230 kilometers per second. That's over 800,000 kilometers per hour, fast enough to cross the United States in about 5 seconds. At this speed, it takes the Sun roughly 225 million years to complete one full orbit around the galactic center. Astronomers call this a galactic year. The last time the Sun was in this position in its orbit, dinosaurs had just begun to emerge on Earth. When we complete this current orbit and return to this same spot, 225 million years from now, who knows what Earth will look like, or if humans will still exist to wonder about it. Every star in the disk is on a similar journey, all orbiting at speeds that depend on their distance from the center. And while each star is tiny compared to the galaxy as a whole, collectively their mass adds up to something significant, 100 billion solar masses that definitely contribute to the overall gravitational field. But stars aren't the only visible matter in the disk. Filling the spaces between stars is the interstellar medium, the ISM, a vast sea of gas and dust that makes up a surprisingly large fraction of the galaxy's visible mass. The ISM is mostly hydrogen and helium, the simplest and most abundant elements in the universe. But it exists in wildly different states. In some regions, you have cold molecular clouds, dense, dark regions where the temperature drops to just 10 or 20 degrees above absolute zero. In other regions, you have hot ionized plasma, heated to millions of degrees by supernova explosions and intense stellar radiation. The total mass of gas in the Milky Way's disk is somewhere between 10 and 15 billion solar masses. That's less than the stellar mass by a factor of about 7 or 8, but it's far from negligible. This gas represents a significant gravitational contributor, especially in certain regions. Where does this gas concentrate? Primarily in the spiral arms, those beautiful, glowing structures that define the appearance of spiral galaxies. The spiral arms are actually density waves, regions where gas compresses and triggers the formation of new stars. The gas doesn't permanently stay in the arms, but it gets compressed as it passes through them, leading to bursts of star formation that light up the arms brilliantly. These star-forming regions, places like the Orion Nebula that you can see with binoculars, are where the ISM is at its densest and most active. Giant molecular clouds collapse under their own gravity, fragmenting into thousands of new stars over just a few million years. But even outside the spiral arms, gas permeates the entire disk. Thin atomic hydrogen fills the space between denser regions, and astronomers can map this hydrogen by observing the 21 centimeter radio emission line that neutral hydrogen naturally emits. This is actually how we measure rotation curves in distant galaxies. Stars are too faint to track individually in faraway galaxies, but we can detect their hydrogen gas using radio telescopes. By measuring the Doppler shift of the 21 centimeter line, we can determine how fast the gas is rotating at different distances from the galaxy's center. And here's what we find. The gas follows the same rotation pattern as the stars. It moves in roughly circular orbits, rotating around the galactic center at speeds that stay surprisingly constant across huge distances. The gas sees the same gravitational potential the stars do and responds to it in the same way. Together, the stars and gas make up the visible disk, about 110 to 115 billion solar masses of ordinary matter, all rotating in an organized plane around the galactic center. Now comes the crucial question. Is this enough to explain the rotation curves we observe? To understand how much visible matter contributes to stellar motion, we need to break the galaxy down into zones and see what dominates where. Let's start in the very center, within about 3 kiloparsecs, or roughly 10,000 light-years, of the galactic core. Here, the bulge dominates. Those 20 billion solar masses of densely packed old stars create a strong gravitational field that controls the motion of everything in the inner galaxy. Dark matter is present here too, but the visible matter in the bulge is dense enough that it's the primary gravitational player. Move outward into the mid-galaxy region, from about 3 to 15 kiloparsecs, or 10,000 tons to 50,000 light-years from the center. This is where the disk dominates. The 100 billion solar masses of disk stars and the 10-15 billion solar masses of gas are spread across this region. Here, the visible matter matters. It provides a significant portion of the gravitational force controlling stellar orbits. But even here, it's not the whole story. Dark matter is present throughout this region too, and it contributes substantially to the gravitational potential. The visible matter provides the gravitational field you'd calculate from the stars and gas alone, but dark matter quietly adds more. Then move to the outer galaxy, beyond 15 kiloparsecs, or 50,000 light-years from the center. Out here, visible matter becomes increasingly sparse. The stellar disk thins out, the gas density drops, and what little visible mass remains simply can't account for the gravitational forces needed to explain the observed rotation speeds. This is dark matter territory. The halo dominates completely. Now, here's the critical insight. If visible matter were all that existed, what would we expect to see? We'd expect the rotation curve to rise steeply in the inner regions where the bulge and disk are densest, peak somewhere in the middle, and then decline steadily as you move outward into regions where visible mass thins out. Just like planetary orbits, the farther out you go, the slower the orbital speed should be. This is what Newton's laws predict. This is what makes intuitive sense. But that's not what we observe. Instead, we see the rotation curve rise, then flatten out and stay flat far beyond the visible edge of the galaxy. Stars in the outer regions are moving way too fast for the visible matter alone to explain. Let's make this concrete with numbers. Our Sun sits about 8 kiloparsecs from the galactic center, 26,000 light-years, right in the middle of the disk. At this position, if you calculate the orbital velocity based solely on the visible matter, the 20 billion solar masses in the bulge, the 100 billion in the disk stars, the 10-15 billion in gas, you get an expected velocity of roughly 160 kilometers per second. But our actual observed velocity is 230 kilometers per second. That's a difference of 70 kilometers per second. That's the missing velocity that visible matter can't explain. And that missing velocity is provided by dark matter. Even here, at the Sun's position in the middle of the visible disk, dark matter is contributing nearly a third of the gravitational force controlling our orbit. The visible matter provides maybe 160 km worth of orbital velocity. Dark matter adds another 70 km on top of that. This pattern continues across the entire galaxy. Visible matter dominates the inner regions and contributes significantly in the mid-regions, but dark matter is always there, always adding to the gravitational potential, becoming increasingly dominant as you move toward the outer edges. So here's the complete picture of what controls stellar motion in our galaxy. 3 distinct components, each dominating at different scales. First, the bulge, concentrated ancient stars packed into the innermost few thousand light-years. These stars are billions of years old, formed in the galaxy's early history. They orbit chaotically in all directions, their collective mass creating the strong gravitational field that dominates the central region. Second, the disk, younger stars and gas spread across a vast rotating plane. This is where most of the star formation happens today, where spiral arms sweep through space, where our Sun makes its 225 million year journey. The disk contributes significantly to the gravitational field in the mid-galaxy regions, providing the mass that keeps disk stars on their orderly circular paths. Third, the halo, the invisible dark matter sphere that extends far beyond the visible galaxy. This is the largest component by far, containing perhaps 10 times more mass than all the visible matter combined. It provides the gravitational scaffolding that holds everything together and becomes completely dominant in the outer regions. Each component matters at different distances from the galactic center. Each contributes to the overall gravitational potential. And the combined effect of all three, bulge plus disk plus halo, is what creates the flat rotation curve that originally puzzled astronomers. You can't explain the rotation curve with any single component, you need all three. The visible matter is crucial in the inner and mid-galaxy. The dark matter is crucial everywhere, but especially in the outer regions. Together, they create the gravitational potential that every star responds to. But there's something we haven't talked about yet, something subtler, something that affects stellar orbits in ways that don't show up in the smooth average rotation curves we've been discussing. Because the galaxy isn't actually smooth. It has structure, it has spiral arms that sweep through space, it has a bar at the center, it has satellite galaxies orbiting around it, tugging gravitationally as they pass. These structures don't just sit there passively, they interact with stars, perturbing orbits, creating patterns, shaping the galactic disk in ways that the simple picture of a smooth gravitational potential can't capture. And when we look closely at these effects, we discover something fascinating. The galaxy is far more dynamic, far more chaotic, and far more interesting than the rotation curves alone would suggest. There are subtler forces at work in our galaxy, forces that don't show up in the smooth rotation curves we've been discussing, but that profoundly affect the paths individual stars take through space. We've covered the big picture: dark matter providing the invisible scaffolding, visible matter contributing mass throughout the disk, the bulge dominating the center, the supermassive black hole sitting as a passive passenger. These are the main gravitational players. But the galaxy isn't a featureless blob of matter. It has structure, beautiful, complex, dynamic structure. And that structure interacts with stars in ways that the averaged, smoothed-out rotation curves completely miss. There are spiral arms sweeping through the disk like cosmic tsunamis. There's a massive bar at the center, rotating like a rigid spoke. There are dozens of smaller satellite galaxies orbiting the Milky Way, tugging gravitationally as they pass. And all of these features perturb stellar orbits, pushing and pulling on stars over millions of years, creating patterns and effects that only become visible when you look closely. So what are these hidden forces? How do they shape the motion of stars? And how do they fit into the complete picture of what controls stellar motion? Let's explore the hidden framework that gives our galaxy its intricate structure. When you see a picture of a spiral galaxy, like Andromeda or the Whirlpool Galaxy, the most striking features are the spiral arms. They look like solid structures, like cosmic whirlpools of stars frozen in space. It's natural to assume they're permanent features, bands of stars that stay together as they orbit. But that's not what spiral arms are at all. Spiral arms are density waves, regions where stars, gas, and dust temporarily crowd together. They're not made of any particular group of stars. Instead, they're patterns that move through the galaxy, and individual stars drift in and out of them over time. Think of it like a traffic jam on a highway. The jam itself, the region of slow-moving, densely packed cars, can persist for hours and even move backward along the highway as new cars enter from the front and cars leave from the back. But no individual car stays in the jam the whole time. Cars enter, slow down, bunch up with others, then accelerate and leave. The traffic jam is real, but it's not made of any specific set of cars. Spiral arms work the same way. Stars enter an arm, slow down slightly due to the increased gravitational pull from all the other stars and gas crowding there, spend a few million years passing through, then exit out the other side. The arm persists, but it's always made of different stars. Here's the weird part. The spiral arms rotate around the galaxy at a different speed than the stars do. The arms have what's called a pattern speed. They rotate as if they were a rigid structure, all parts moving at the same angular velocity. But stars at different distances from the galactic center have different orbital speeds, so sometimes a star is moving faster than the arm pattern and overtakes it. Other times it's moving slower and the arm sweeps past it. The arms aren't just passive density enhancements though. They gravitationally perturb the stars that pass through them. As a star enters an arm, the concentrated mass pulls on it, slightly altering its orbit. The effect is small. The star's path bends by maybe a few degrees, but over millions of years and multiple arm passages, these perturbations add up. And there's another crucial effect. Spiral arms trigger star formation. When gas clouds enter a spiral arm, they get compressed by the increased density. This compression can trigger gravitational collapse, fragmenting the clouds into thousands of new stars. That's why spiral arms shine so brightly. They're lit up by young, massive stars that formed right there in the arm. The spiral arms aren't controlling the overall rotation of the galaxy. They're not one of the major gravitational components, but they are sculpting the fine details of stellar motion, creating structure, triggering birth, and adding a dynamic element that makes the galaxy far more interesting than a simple smooth disk. But spiral arms aren't the most dramatic structural feature of our galaxy. That honor goes to the galactic bar, a massive, elongated concentration of stars that extends through the center like a cosmic spoke. For a long time, astronomers weren't sure if the Milky Way had a bar. We're inside the galaxy, after all, and it's hard to see the big picture from the inside. But observations over the past few decades have confirmed it. The Milky Way is a barred spiral galaxy with a prominent bar structure at its center. This bar contains roughly 10 billion solar masses, about 10% of the total stellar mass in the galaxy, and it's big, extending approximately 5,000 light-years from one end to the other. If you could view the Milky Way face-on from outside, you'd see this bar cutting through the center, with spiral arms attached to its ends. Unlike spiral arms, the bar really is a rigid structure. It rotates as a solid body, all parts moving together. The bar has a pattern speed of about 39 kilometers per second per kiloparsec. That might sound like a strange unit, but it tells you how fast different parts of the bar are moving. Stars closer to the center move slower in absolute speed. Stars farther out move faster, but they all complete one rotation at the same time. There's a special radius called the coronation radius, about 6,100 light-years from the center, where stars orbit at exactly the same speed as the bar rotates. At this distance, stars and bars move in lockstep. Inside the coronation radius, stars orbit faster than the bar. They zip past it, encountering it periodically as they overtake the slower-moving bar structure. Outside the coronation radius, the bar rotates faster than the stars. It sweeps past them, and stars experience the bar as a wave that periodically rushes by. Why does this matter? Because the bar creates strong gravitational perturbations. As stars encounter the bar, whether by overtaking it or being overtaken by it, the bar's elongated mass distribution tugs on them, changing their orbits. Some stars gain energy and move to higher orbits. Others lose energy and sink toward the center. The bar is particularly effective at funneling gas toward the galactic center. As gas clouds encounter the bar, they lose angular momentum and spiral inward, feeding star formation in the central regions and potentially feeding the central black hole during active periods. The bar also affects the overall structure of the disk. It can create resonances, special orbital configurations where the bar's influence reinforces itself over many orbits. These resonances sculpt the distribution of stars and gas, creating gaps and overdensities at particular radii. Our Sun is probably outside the bar's coronation radius, meaning the bar is rotating faster than we're orbiting. Every few 100 million years, as the bar pattern sweeps around, we experience its gravitational influence, a subtle tug that slightly perturbs our orbit before the bar moves on. The bar isn't determining our overall orbital speed. Dark matter and visible mass do that. But it's adding structure, adding perturbations, making our orbit more complex than a simple circle around the galactic center. But even the bar isn't the end of the story. Because our galaxy doesn't exist in isolation, it's surrounded by dozens of smaller satellite galaxies, all orbiting the Milky Way, all tugging gravitationally as they pass. The most prominent are the Large and Small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere. The Large Magellanic Cloud contains about 10 billion solar masses and orbits at a distance of roughly 160,000 light-years. The Small Magellanic Cloud is smaller, maybe 7 billion solar masses, at about 200,000 light-years. But those are just the big ones. Astronomers have now identified approximately 50 dwarf satellite galaxies orbiting the Milky Way. Most are tiny, containing only a few million stars, nearly invisible and discovered only through careful surveys. But they're there, scattered around the galaxy like gnats around a lamp, and every one of them creates gravitational disturbances. When a satellite galaxy passes through or near the Milky Way's disk, its gravity creates a wake, a disturbance in the disk that propagates outward like ripples on a pond. Stars near the passage point get tugged by the satellite's gravity, their orbits perturbed. These perturbations aren't huge for any individual star, but collectively, they can affect large swaths of the disk. Sometimes these encounters are dramatic enough to create stellar streams, long, narrow trails of stars, torn from a satellite galaxy by the Milky Way's tidal forces. These streams wrap around the galaxy, marking the path the satellite took as it was slowly ripped apart. The Sagittarius stream is one example, a trail of stars circling the galaxy, remnants of the Sagittarius dwarf galaxy that's being consumed by the Milky Way. And it's not just current satellites. The Milky Way has been consuming smaller galaxies throughout its history. About 9 billion years ago, a galaxy roughly a quarter the mass of the Milky Way collided and merged with us. Astronomers call this the Gaia-Enceladus merger, after the European Space Agency's Gaia satellite that helped identify the stars from this ancient collision. Those stars are still here, mixed into our halo, orbiting on paths that reveal their violent origin. They have different chemical compositions, different orbital characteristics, signatures of their foreign birth. Every time we analyze stars in the halo, we're seeing evidence of this ancient merger and probably dozens of smaller ones. These satellite interactions don't control the overall rotation curve. They don't set the fundamental orbital speeds, but they sculpt the details. They create substructure. They perturb orbits in complex ways that add richness and complexity to the galaxy's dynamics. So, now we can finally put all the pieces together. What really controls the motion of every star in our galaxy? The answer is everything. Dark matter provides the background gravitational potential, the invisible ocean in which everything else floats. It sets the overall shape of the rotation curve, keeping it flat far into the outer reaches where visible matter thins to nearly nothing. Dark matter is the foundation, the scaffolding, the framework that holds the galaxy together. Visible matter, the stars and gas in the disk and bulge, provides the local gravitational field that stars interact with on short timescales. It controls the day-to-day orbital evolution, the immediate gravitational forces that any given star experiences. In the inner and middle regions of the galaxy, visible matter contributes significantly to orbital velocities. The supermassive black hole at the center is effectively irrelevant except for the handful of stars orbiting within a few light years of it. For the other 200 billion stars in the galaxy, including our Sun, the black hole might as well not exist. It's a passenger, not a driver. The spiral arms provide periodic perturbations, nudging stars as they pass through, triggering star formation, adding dynamic structure to the disk. They don't control the big picture, but they sculpt the details. The galactic bar creates strong perturbations in the inner galaxy, funneling gas, creating resonances, affecting orbital evolution over hundreds of millions of years. Satellite galaxies add long-term disturbances, creating tidal streams, perturbing orbits during close passages, and occasionally merging entirely and reshuffling the stellar populations. Every star responds to all of these forces simultaneously. The orbital motion of any given star is an emergent property, not dictated by any single source, but arising from the combined gravitational influence of everything around it. It's not a hierarchy, with one force in charge and others as subordinates. It's a democracy. Every piece of mass votes, and the result is the complex, beautiful dance of stellar motion we observe. If you wanted a simple answer, if you wanted to know what single thing controls the motion of every star, I have to tell you, there isn't one. It's a symphony, not a solo. Dark matter is like the concert hall itself. It provides the acoustic properties, the fundamental structure that allows everything else to make sense. Without it, the whole performance falls apart. The outer stars would fly away, the rotation curves would plunge instead of staying flat. Dark matter sets the stage. Visible matter is the orchestra. The stars and gas are the instruments creating the melody, the harmonies, the complex interplay of notes that make up the music you actually hear. They provide the mass that stars interact with most directly, the gravitational forces that shape orbits on human comprehensible timescales. The supermassive black hole? It's maybe a single violin in the back of the orchestra. If you're sitting right next to it, it's the loudest thing you hear. But from anywhere else in the concert hall, it blends into the background, one voice among hundreds, barely noticeable in the overall symphony. The spiral arms are like the rhythm section, providing periodic beats that structure the music. The bar is a recurring motif that shapes the composition. Satellite galaxies are unexpected flourishes that add complexity and surprise. And every star's path through the galaxy is determined by everything else. Every kilogram of dark matter in the halo, every star in the disk, every gas cloud in the spiral arms, every satellite galaxy passing nearby. They all contribute, they all matter, they all have a gravitational vote in determining where each star goes next. The motion of stars isn't dictated from above by some central authority. It emerges from the collective gravitational influence of everything in and around the galaxy. It's the result of gravitational democracy, every piece of mass pulling on every other piece, and the observed motion is the compromise that satisfies all those pulls simultaneously. This is what's really controlling the motion of every star, everything. The universe, it turns out, is far more collaborative than we thought. There's no puppet master pulling strings from the center. There's no single force responsible for everything. Instead, it's a complex interconnected system where every component influences every other component. And the beautiful structure we observe, the spiral arms, the flat rotation curves, the organized disk, emerges from the interactions of all those components working together. Every star you see tonight is moving in response to forces near and far, visible and invisible, obvious and subtle. The star orbiting a few light years from you is pulling on you gravitationally. So is the dark matter passing through your body right now. So is the supermassive black hole 26,000 light years away, even if its influence is infinitesimal. So are the Magellanic Clouds hundreds of thousands of light years distant. You are connected to everything in this galaxy through gravity, and so is every star. The motion of the stars isn't a mystery to be solved with a single answer. It's a story of collaboration, emergence, and complexity. A reminder that the most interesting phenomena in the universe arise not from single dominant forces, but from the intricate interplay of many forces working together. And if that changed how you think about the universe, if you now see galaxies not as simple structures controlled by their centers, but as complex democratic systems where every piece matters, then maybe hit that like button and subscribe, because there's so much more to explore. The universe is more beautiful, more complex, and more collaborative than most people realize. And now you know the truth about what's really controlling the motion of every star.